Okay, our last speaker is Digjoy Paul from Indian Institute of Science. His talk title is Birch Correspondence and Shape of Graphs. Please, Digjoy.
Thank you. Thank you to the organizer for inviting me and giving me a chance to talk here. This talk is based on a joint work with Joseph Pape and Professor Anna Sealing. And the next 15 minutes, I will be talking about the Birch correspondence and shape of graphs. So the Birch correspondence, in this paper, William Birch gave 4 variants of RSK correspondence, which provides bijective proofs of 4 Retilude identities. Among of them, we choose the third on that paper, which gives a bijection between simple label graphs and semi-standard Young tableau of threshold shape. Let us come to detail. So here is one example of simple label graph with vertices on 1, 2, 3, 4. And the degree of a vertex is the number of neighbor of it. So the degree sequence is degree of 1, 2, 3, 4, etc. So in this example, it is 2, 3, 2, 1. And to each graph, we associate one monomial that is obtained by taking product of xi power di. So in this case, it is x1 square, x2 cube, x3 square, and x4. Sorry, I cannot proceed. Okay. Now, if we try to obtain the generating function for all simple graphs, it is easy to see that sum of over all these monomials is a symmetric function in the variable x1, x2, etc. And it's natural to us what is the expansion of this symmetric function in the basis of Schur functions. To define the Schur function, we need semi-standard Young tableau. So starting with, you have a partition and you draw its Young diagram. So in this example, we have 3, 2, 2, 1 is the partition, and you draw 3 boxes on that first line, then 2 boxes, then 2 boxes, then 1. And this color thing indicates the special kind of partition, which is called threshold. Here, this means that if you flip the blue thing through the main diagonal, you will obtain the remaining shape, exactly same shape. And by a semi-standard Young tableau, we mean you fill the Young diagram weakly in the rows and strictly on the columns. And the underlying partition is called the shape of it, which is 3, 2, 2, 1. And the weight is number of 1s, number of 2, number of 3, and number of 4. So here are 3, 4 in the Young tableau. So the weight of it is 3. And the monomial we associate to each tableau is obtained alike, is x power weight of it. So it is x1 square, x2, x3 square, x3. So now one can ask about the generating function, and the Schur function is the generating function for the semi-standard Young tableau for a particular shape. And the Retilude's identity gives you the required expansion. And William Birch, by providing a bijection between graph and semi-standard Young tableau of threshold shape, gives a bijective proof of this identity. Okay. Now, threshold partition are an important topic, as is shown. Like from the Birch correspondence, it can be proved that threshold partition are the maximal among the graphic partitions. Graphic partitions are the partition which are degree sequence of some simple graph. And the Garza proved that this criteria, that given any sequence, it is graphic if and only if it is dominated by some threshold partition. This is equivalent to the Erdős-Garley theorem. This is the work of Garza. Okay. And a simple graph is called threshold if the associated partition is threshold. So like in the figure B, the partition is this depicted in figure A, 3, 2 to 1. So it is threshold. But the figure in figure C and figure D, those are not threshold graphs. As you can see, the degree partition is just 2, 2, 1, 1, which is not a threshold. Okay. So the next thing that I need to mention about is the word of instead. So given a word in alphabet, it is a nice problem to find the length of the longest increasing subword, and it's connects to many important areas of mathematics. So given the word 2, 1, 3, 4, 2, 1, 2, 3, you can check the longest increasing subwords are 1, 1, 2, 3, 2, 2, 2, 3, 1, 2, 2, 3. To answer this question of finding the length of the longest increasing subword, Sinstead came with this beautiful theorem, algorithm. Okay, this Sinstead algorithm takes a word as an input, and by an algorithm, which I will come into the next slide through example, it insert the letters into the empty tab, into the empty shape, and so obtained things is called semi-standard tableau, and the shape of that tableau is called shape of the word. And in 1961, he proved that the length of the longest increasing subword is the biggest row of the tableau so obtained from the word. For example, the word 2, 3, 1, 2. Now you insert 2, so you place one box. Then to insert 3, since 3 is bigger than 2, you put 3 just after it. When you again insert 2, this 2 you cannot place after 3, so you bump the 3 and 2 placed on that place. So it becomes 2 to 3. And when you insert 1, it will bump the first 2 on the first row, and 2 will bump on the second row. There is a 3, and it will bump to the third row. Finally, in inserting 2, you will have this tableau 1, 2, 2, 2, 3. So for this word, the longest increasing subword, the length is the first row length is 3. Okay. So to start the bar correspondence, given a simple graph, we first define what is called the bar array. We want to arrange the edges of the graph in the following manner, that the top in each column, the top element AK is bigger than the corresponding bottom element. And when two elements in the bottom are equal, then on the top there will be strictly less than equal to sign. Yeah, when AK equals to AK plus 1, then on the bottom you will have strict signs, strictly better. So for example, for this graph, the edges are 1, 2, 2, 3, 1, 3, 4, 2, etc. So for the bar array, we'll arrange the edges in the following manner. We'll write first 2, 1, then 3, 2, 3, 1, and then 4, 2. So for the algorithm, this is the first step. Now we use the Sinstead algorithm together with one recording things. So remember, in RSK correspondence, given a word, you obtain a pair of tableau where you insert and record into different tableau. But in contrast, here we'll insert and record two letters at once to a single tableau. So first we'll insert the bottom row element 1 using Sinstead algorithm. So it will come here 1. Now to record it, there is a unique place just adjacent to 1, so that the final thing becomes a threshold say partition. So 2 will put just below of 1, not right of 1, right? Then this next stage is 3, 2. So we'll insert 2 and record 3. So 2 will place just after 1. So the tableau becomes 1, 2, 2. Now to record 3, we have only one option, that is to putting 3 below of 2. So that this blue shape and the white shapes, they fit inside. Okay. Similarly, you insert 1, so 1 will bump 2, 2 will place after 2, and then you have to record the 3 on the third row, second column. Okay. Finally, when you insert 2 and 4, you obtain this tableau. So this is the Varge algorithm where recording and inserting happens at the same time. Okay. So analogous to the case of words and insertion tableau, here we define the shape of a simple graph as the shape of the semi-standard tableau obtained by Varge algorithm applying on G. And one can observe that if the graph is itself threshold, then the shape is just the degree partition of it, rearranging the degree sequence. And a simple graph is called hook graph if the shape is a hook partition. So we are interested to characterize the shapes. That given an input, can you decide what is the shape of it? Okay. So what is the shape of tree to begin with? So in figure C and figure D, we have two trees, and we wrote for you two corresponding bar arrays, 3, 1, 4, 2, 4, 1, and 2, 1, 4, 3, 4, 2. And the associated tableau is for the first tree is have a hook shape, but for the second tree doesn't have a hook shape. So we conclude that a tree may not have the hook shape always. So we gave a necessary condition when does the connected graph have hook shape. And in particular, we say that the only connected hook graphs are trees. That is our first result. But to give a necessary and sufficient condition, we define criteria, what is called peak and valley. So for example, in this bar array 2, 1, 4, 3, 4, 2, you see in the below you have a peak thing. 1 goes up to 3 and then comes down to 2. So, but there is one associated result. We need that this 2 on the first row is less equal to the 3 in the bottom row. So the definition says that the bi less equal to bk, and j is the minimum index with bk less than bj, and ai less equals to bj. So in example 1, this graph has a peak, but in example 2, this graph doesn't have a peak because this 3 is not the minimal one which satisfies the condition. So if I remove this 5, 3 edge from the graph, then there will be no problem. But for this 5, 3 in the array, this graph doesn't have a peak. On a similar note, we have another condition called valley of a graph, and and the condition is bj less equal to bk less than aj. And so I am starting with ai bi aj bj and ak bk, and for those I have some criteria. And these following two graphs, one have valley, one doesn't have a valley. And our final theorem says that the shape of a simple graph is hook if and only if its barge array is peak valley free. And the remark is that this theorem is analogous to the statement for RSK correspondence, that when does the word corresponds to a tableau with single row. So this is the analogous result to it. So this is the first step towards the symsted result. And from the main theorem, the corollary is all star graphs are hook graphs. Star graph means you have at some point you have all the vertices joined to it. And so in last two talks, there are some work on crystals. So in this work, on the peak and valley free barge arrays, we defined the stem bridge crystal structure on it by defining the lowering and the Fi and Ei operator on it. And in this crystal, the extremal vectors are the threshold graph of hook set. And by this crystal isomorphism, so this crystal structure gives a isomorphism between set of all peak valley free barge array and semi-standard Young tableau of threshold set, hook set. Thank you for your attention.